Welcome to a high-capacity, cutting-edge episode of Fully Charged. It was a great privilege to visit the Department of Materials at the University of Oxford earlier this year. I was shown around by Professor Peter Bruce, who has spent the majority of his academic career developing the next generation of electricity storage systems. I had a suspicion he might know some actual facts about batteries.
So there are basically two types of batteries. You have a primary battery, which is the sort of thing you buy, put in your radio or something, and then when it's finished, you just throw it away or recycle it. And then there's the secondary battery, which can store electricity. So you can pump electricity into it. Chemical reactions take place inside the battery that store that electricity, and then when you want the electricity back, you can release it back from the battery to power whatever device you want. Those are the ones that perhaps are gaining the most interest right now, because those are the ones that really lie behind the huge success of portable electronics such as the iPad or whatever, and of course electric vehicles, and will be important in storing renewable electricity on the grid in future as we move to more low carbon electricity generation.
Right. Historically, the most recent innovation in that is lithium-ion. Am I correct in saying that?
Yeah, absolutely. I mean, lithium-ion represented a huge breakthrough in the battery industry. I mean, we have to bear in mind there's no Moore's law in energy storage.
That's one of the things I was going to ask. Yeah.
So we're not going to double energy density, store energy storage every 18 months. In fact, it's probably only increased 5 or 6-fold in many decades.
Right.
And so the lithium-ion battery, which more or less doubled energy density, was a major breakthrough and was certainly one of the key drivers behind the portable electronics revolution that we take for granted these days. And it's because lithium-ion batteries have a higher energy density than alternative batteries. In other words, they store more energy per unit mass and per unit volume. And that's, for many applications, that's what matters. There are many characteristics of a battery that matter. Energy density is one of them, but you want to be able to charge it rapidly. Of course, you want it to last as long as possible. You want it to be safe, which is important.
Burst into flames.
Absolutely. Yeah. You want it to be able to cycle many times, so you can charge and discharge it many times. And of course, with a lot of consumer electronics products, we often change the product before we change the battery because we want a new generation of whatever it is. But when you move to things like electric vehicles, and for grid scale storage even more, then the economics say that you really need that battery to last a lot longer than a couple of years. And that's one of the challenges that lithium-ion batteries face.
So how much lithium is there in a lithium-ion battery?
So one of the first things that's I think important is that there's no lithium metal in a lithium-ion battery.
Right.
So lithium, many people are familiar with it, lithium, throwing it into water and it fizzes. That's lithium metal. There's no lithium metal in a lithium-ion battery. The compounds contain lithium as one of the elements in those compounds. I think the general consensus is that there isn't really a major problem that we can expect in terms of running into a shortfall of lithium compounds to make lithium-ion batteries. In fact, it's probably at the current lithium-ion batteries in portable electronics use cobalt. And cobalt is probably a more critical element in that sense in terms of cost, certainly. But no, going forward in terms of the lithium batteries of the future, I don't think we have to be too concerned about scarcity. Of course, it's clearly important to recycle them. And in some ways that becomes a little easier with the new markets of electric vehicles and grid scale storage, because you would never consider just throwing those sort of things away. You would always recover, recycle vehicles and certainly recycle major plant. The elements that go to make up these lithium batteries will be kept within the sort of sphere of their use, recycle and reuse more probably in the future than has been true in the past.
Do you see a potential technology, a variant of the technology we're using now, that could increase energy density?
I think that we will see that. It's interesting because I think we have to remember that we've had the internal combustion engine for over 100 years, and it didn't get to where it is now in 5 or 6.
No.
And we're really reinventing the powertrain in vehicles when we go to electric vehicles. It's a real step change, and it will take time to really reach an optimum level of performance. And the battery undoubtedly is one of the most critical elements. It's one of the real barriers to progress with electric vehicles. And you're right, although there are many things like how fast we can charge it and how long it will last, probably the greatest of all is two things: safety and the range. I think range anxiety is one of the issues. And I think that that's why the plug-in hybrid actually offers a good, at least interim situation, because it removes the anxiety issue. But most of us commute no more than maybe 15, 20 miles to work in Europe. And so if you have a battery that will last even that length of time, or that distance, you could do most of the commutes on that. And that would have a massive impact on reducing carbon emissions, and still have you can do the 300, 400 mile
Can I
drive.
drive to Scotland?
Exactly.
It's a very common question.
Exactly. But I would see that really as a stepping stone as we see battery technology evolving. And we will see new generations of batteries, lithium batteries, coming along that will give us longer range. Frankly, in a lot of these storage challenges for electric vehicles and for the electricity grid in the future, we don't really have energy storage technologies, including batteries, that are fit for purpose.
Right.
And the reason we don't have, in many cases, these technologies is that we still don't understand enough about the underlying science.
Right.
So we can go so far by optimizing on what we know, and we can certainly improve technology, and that's happened. But to take that real step forward, to get that battery that will last a lot longer before it has to be recharged, charged much faster, in many senses we lack understanding of the underpinning science. And if you think about it, we've learned a lot about the natural world, but we probably don't know far more than we know about the nature of life.
Yes.
And so things like energy storage come along. Probably 30 years ago, we didn't really care too much about it. They define problems that actually define areas of the natural world that we have to understand better. And so it challenges us as scientists to explore the chemistry, the electrochemistry that goes on behind these devices, and try to use that knowledge to develop improved technologies, new generations of lithium-ion batteries that will increase the range of electric vehicles.
So you're talking on sub-microscopic levels, super tiny.
Yes, and it's partly because the major part of developing advances in lithium-ion batteries comes down to discovering new materials with new properties or combinations of properties. And that is all about controlling at the atomistic level, producing new compounds where you put atoms together in different combinations to produce different structures at the atomic level, and then realizing by doing that materials that combine properties that we didn't perhaps have before. So materials, as I said, that will store more lithium ions, and that's what controls largely how much energy we can store in the device, but do so perhaps with greater lithium-ion mobility inside the solid. So one of the things that controls how fast you can discharge and charge a battery is how fast these lithium ions, these positively charged lithium atoms that zip in and out of the electrode as you charge and discharge, how fast they move. So you want them to move fast. At the same time, you want to get a lot of them in there, because in a lithium-ion battery, you basically move lithium ions from one electrode to the other. Like any battery, you have two electrodes, a negative and a positive, and an electrolyte in between. And you move lithium ions from one to the other as you charge and back as you discharge. So the more lithium ions you can stuff into these things, the more charge, the longer you can drive. And the faster you can move them, the faster you can recharge. So that's a bit of a sort of broad simplification, but it gives you a sense of that intimate interaction between the performance of your vehicle and actually what's really going on at the atomistic level. One of the key issues for electric vehicles is also cost. Lithium-ion batteries are too expensive. And the current lithium-ion battery that I have in my mobile phone uses cobalt in the positive electrode. Now, cobalt is expensive. And that is reasonably acceptable for a product like that.
Because it's a small
one, you don't have a lot of material in there. But if you think about the size of a battery in a vehicle, or even more, if you think about grid scale storage, where you have large installations, then it just becomes not viable with expensive elements. Now, that therefore challenges us. Can we get materials that will perform as well as those materials based on cobalt, but using, for example, iron or manganese? Iron and manganese, can you make electrodes from rust?
Yes.
This
would be very good, wouldn't it?
I mean, one of the electrode materials that we're looking at here, is basically a lithium iron silicate. So literally, can you make electrodes from rust and sand? Really low cost, materials. Now you also have to be able to process them at low cost, and of course they have to have all the properties that you need. But you know, these are the things that we now have to think about that perhaps a few years ago didn't really come into the equation, because there's no one size fits all to the storage of electricity on the grid. And I think energy storage, you know, as we're now seeing with the increasing deployment of wind farms, you know, people are recognizing that the wind doesn't blow continuously, solar doesn't help you at night. Storage is going to be not the only solution, but part of the solution to making those, you know, clean grids, those low carbon grids work in the future.
Peter, thank you so much.
Not at all. Pleasure.
Really good talking to you. Thank you very much. I then wandered down some corridors of the Materials Science Department looking for some PhD students who had some interesting projects. So explain this then, because I recognise those cells in that one.
Yeah, exactly. So these are the same cells. They're called 18650, and that's because of their size. They're 18 millimeters in diameter and 65 millimeters long. And I don't know about the zero. Chris isn't told me yet.
But that explains it. I never knew why that number, so there we go.
There we go, yeah. So, and same with that other cell. That, it's all about the numbers,
it's about the size
of it.
Right.
Yeah,
right.
Exactly. So these are from old laptop batteries that Chris took apart, and we found through Chris's research that over half of the laptop batteries that we examined, there are cells that are still usable, meaning more than 60% of the capacity left. And that's massive for small scale or even off-grid energy storage, where you don't need like perfectly healthy cells. You just need something to be there.
But I mean, and when you say that, those laptops then were considered finished rubbish.
Exactly, yeah. They were in the dump. What we're going to do is harvest these useful cells and recombine them into a useful small-scale energy storage device designed for developing countries. So this guy is our little demo unit that Chris and the boys put together, and that lights up our little light, and it's perfect. So
I can guarantee there's no wires secretly hidden. It's definitely working from that. Right. Can you kind of control the stress on those batteries by the software, thereby lengthening their life further? You know?
Yeah. So yeah. Great question. So for this, they won't be nearly as stressed as much as they are in a car. You're right. Like cars is going to like hammer them. For LED lighting, it's very, very low power. But on top of that, what we're doing is our algorithms are detecting the state of health of each cell, and then loading each cell proportional to its remaining capacity. So then the weaker cells are getting like slightly less current than the more healthy cells. And that way, they should degrade at the same rate and last longer. And we're going to be extracting all of the energy storage capability out of every single cell.
Fantastic, guys. No, thank you very much. That's been really good. And really, I think it's fair to say, important work that you're doing. That will benefit a lot of people. So congratulations and well done.